The lift curve is a significant way to illustrate the properties of an airfoil under various conditions and in various configurations. The curve plots coefficient of lift CL against the angle of attack alpha. You may deduce from the locally looking carefully at this curve at far as a symmetrical airfoil. Since it starts with a zero lift at the axis origin, the curve for positively cambered airfoil would actually have its zero lift point to the left of the CL axis, since the zero lift alpha for such an airfoil is typically minus 4 degrees. The CL increases with angle of attack up to a maximum CL max, which corresponds to the critical angle of attack, above which the lift decrease sharply, a phenomena in the significant lesson is covered. There is several important facts that become evident from the study of lift curve in association with the lift equation. To maintain a constant lift force, any change in dynamic pressure must be accompanied by the adjustment in the angle of attack. For a constant lift force, each dynamic pressure requires a specific angle of attack. Minimum dynamic pressure is determined by the CL maximum, which occurs at specific angle of attack, the critical angle, which is between 14 and 16 degrees depending upon the aerofoil. The angle of attack for CL maximum is constant for a given configuration. If more lift is required because of greater weight, a greater dynamic pressure, that is more speed, is required at given angle of attack. The greater the weight, the higher will be the minimum dynamic pressure or speed required for the level flight. The lift formula can be used to obtain the data, which can be used to apply the lift curve, but this can also apply only properly be done. If the specific values to be used are converted to SI units to calculate speeds, we need to rearrange the lift formula to read the velocity equals the square root of the ratio of lift to the dynamic pressure and the wingspan. If the aircraft mass is 60,000 kgs, we need to multiply that by the force of gravity 9.81 meter per second square to achieve the weight, which will be the same as the lift balancing it. This result as 5,88,600 Newton if we convert that to high speeds. A high CL maximum is only one of the requirements for all an airfoil section, but it's the main point is that it gives a minimum flight speed. With the low VS comes the penalty of the low efficient cruise speed because of an excessive drag generated. It is thus better to use an airfoil that is efficient at high cruise speed with an ability to increase the camber temporarily. When it is necessary to fly slowly, such as an approach, this can be achieved by the use of hinge sections of the wing trailing edge and the leading edge, collectively known as the flaps. The lift curve can be used for the information about the aerofoil characteristics, and when used in conjunction with the lift formula can give the further useful data. The lift curve will be seen again soon in the lift session, but in combination with the counterpart drag curve. As you will see, the drag is inseparable from the lift.